So picture this. It's 1986, and one of the greatest minds in physics makes this incredibly bold 50-year prediction. It wasn't about some new discovery or a new experiment. It was about an idea, a bet on whether a really radical new theory would even still matter a half-century down the road. That theory was string theory, and folks, the clock on that bet is just about to run out.
And here it is. This is the prediction. A young physicist at the time, a guy you might have heard of named Brian Greene, he asks the legend himself, Edward Witten, if string theory is just another passing fad. And Witten's response was just so simple, so confident. He just said, 50 years from now, people will still be talking about string theory. Now that might sound simple, but believe me, this was a massive bet on the entire future of physics.
Okay, so let's just lay this out. The prediction was made back in 1986. That means the big 50 hits in 2036. We are in the final stretch. I mean, the clock is seriously ticking. And the big question is, after all this time, was he right?
To really get the weight of that prediction, you've got to transport yourself back to 1986. At major places like Harvard, the environment was, as Brian Greene himself put it, not particularly supportive of string theory. I mean, to most people, it was seen as totally outlandish, way out there. So for Witten to have that kind of confidence, well, that was a pretty defiant stance against the entire physics establishment.
So what is this wild idea anyway? You know, at its heart, it's actually kind of beautiful and simple. For centuries, we've pictured the universe's most basic building blocks as these little tiny dots, right? Point particles. String theory just asks a simple question. What if they're not? What if every single particle, an electron, a quark, everything is actually a minuscule, vibrating little filament of energy? A tiny, tiny string.
Okay, so why? Why on earth did physics need an idea this weird? The answer lies in this deep, fundamental conflict right at the heart of how we understand the universe. A problem so big, some have called it the problem of everything.
See, on one side you've got Einstein's masterpiece, general relativity. That's the theory of the big stuff, stars, galaxies, gravity. And on the other side you've got quantum mechanics, the super weird but unbelievably successful theory of the small stuff, atoms, particles, forces. Here's the problem. They just don't get along. They hate each other. As Witten explains it, Einstein's highly nonlinear mathematics for gravity completely falls apart when you try to bring in the rules of the quantum world.
Now you might be thinking, so what? Why bother? Why not just use one theory for the big things and another for the small things? Well, the answer is actually really simple, because big things are made of small things. The sun is just a giant ball of quantum atoms. A black hole, this massive cosmic object, has a quantum-sized point at its very center. To really, truly understand the universe, you need one set of rules that works for everything.
So with this huge problem staring them in the face, what was it about string theory that made physicists think, this is it? This has to be the answer? Well, it wasn't just one single discovery. It was this whole series of what felt like miracles. These moments where the theory should have died, but instead, it just seemed to solve its own impossible problems.
Witten himself describes it like one of those old-timey cliffhanger shows, The Perils of Pauline. He says at every single turn, whenever physicists thought they'd found a fatal flaw, the theory would suddenly reveal some new, hidden trick, a miraculous escape that didn't just save it, but actually made it even more powerful. And that's just shocking, because theories are supposed to break when you push them. This one, it just refused to.
First off, you won't believe this, but they kind of stumbled upon it by accident back in the late 60s. They were trying to describe the nuclear force, and the math kept spitting out this weird extra particle, a particle that looked exactly like the graviton, the particle of gravity. It was like the theory wanted to include gravity. And then came the final miracle, the one that convinced a very reluctant Ed Witten. He'd been pointing out this huge flaw, how the theory couldn't explain this fundamental left-right asymmetry in nature. But then, in 1984, boom, another one of those miraculous escapes solved the problem. For Witten, that was it. The coincidences were just too much to be a coincidence.
And the miracles, they just kept coming. In the 90s, physicists uncovered something called duality. Now, this is a truly mind-bending idea. It means you can have two theories that look completely different, with totally different math, describing what seem to be different universes, and yet they are secretly the exact same theory. It's like finding out that two completely different books, written in different languages, are actually telling the exact same story.
So in 1997, a physicist named Juan Maldacena found the most jaw-dropping example of this. He took a quantum theory that lived in a perfectly flat universe, with no gravity at all. A theory that looks a lot like the one we use to describe particles in our big accelerators. And he showed
that it was mathematically identical, the exact same thing as a completely different universe with extra dimensions and strings and a theory's gravity that looks just like Einstein's. I mean, this was just brilliant. It showed that gravity could literally emerge like a hologram from a theory that didn't even have it to begin with.
Okay, so the theory is, having all these miracle moments, right? It's looking really good. But, and this is a big but, it also came with some really deep, really persistent, and honestly, very controversial puzzles. Problems that still haunt it to this day. And yeah, this is the big one. See, physicists had hoped that string theory would spit out one unique answer, our universe. It didn't, not even close. Instead, it described this vast, vast landscape of possible universes, maybe 10 to the 500th power of them. That's a 1 with 500 zeros, each with its own laws of physics. So, which one is ours? And more importantly, why?
This led to a, well, let's just say a very controversial answer, the anthropic principle. The idea is basically this. Maybe there's no deeper reason our universe is the way it is, other than the fact that it's one of the few where the laws are just right for life to exist. I mean, of course we live here, we couldn't possibly live in one of the other ones. To a lot of physicists, this felt less like a scientific explanation and a lot more like just giving up.
And you know who was one of the people who hated this idea the most? Edward Witten himself. He said, quote, "Literally, it made me very unhappy for years." He wanted a deep, beautiful, elegant reason. But eventually, he sort of made a reluctant peace with it, concluding that the universe wasn't created for our convenience. That's a pretty profound admission about the potential limits of what science can even explain.
So let's bring it all back to that 50-year prediction. With just over a decade to go, where are we? Where do we actually stand? The journey since 1986, it's been nothing like anyone expected.
Back in '86, the thinking was pretty clear. Particle accelerators, those were going to be the places to find the next layer of physics. But nope, that's not what happened at all. We found the Higgs boson, which was great. It confirmed the model we already had. But then, not much else. Meanwhile, cosmology, which was this sleepy little field with just two numbers that weren't even measured very well, it just exploded. It became this incredible precision science, and it revealed that the expansion of the universe is speeding up. The biggest clues came from directions nobody even saw coming.
So where does that all leave us right now? Well, on one hand, string theory is still a purely mathematical idea. It's completely unproven by any experiment. And yet, it has completely revolutionized pure mathematics and given us our absolute deepest insights into things like quantum gravity. But here's the catch. As Witten himself will tell you, its fundamental principles, the why at its very core, are still a total mystery. And all the while, that 50-year clock just keeps on ticking.
So, in a way, Witten was absolutely right, wasn't he? People are definitely still talking about string theory. It has completely reshaped entire fields of science. These incredible ideas like duality and holography, they're here to stay. But is it the final answer, the theory of everything? Or is it just a beautiful, maybe flawed map of a territory we have yet to truly discover? Well, we've got 11 years to find out.